introduction. So the title of the talk today is The Importance, Composition, and Subsurface Characterization of Salt Welds in the Southern North Sea. So Gabriela is a geologist conducting her PhD research in salt tectonics at the Basins Research Group, Imperial College London. She obtained her BSc and MSc degrees in Brazil, where she has also worked in the oil and gas sector as an exploration geologist for the Brazilian Petroleum Agency and for Rosneft. Her research interests focus on sedimentary basins analysis, including salt tectonics and the interplay of tectonics and sedimentation. So Gabriela, the floor is yours.
Thanks so much, Clara. And so I'm going to share my screen to start the presentation. Oops, let me just go to the first slide and not to the rest. All right. So just checking if my screen it's shared and can everybody see the pointer as well?
Yes.
Yeah, that's good, Gabby.
Okay.
Thank you.
Okay. Thank you. So thanks all for joining today. Also, thank you so much for the South Basins Committee for the opportunity to give this talk, in which I will present some results from my PhD project at Imperial College with Professor Chris Jackson. And I would also like to thank Dr. Peter Fitch from University College London for his help with the petrophysical analysis. So what is a salt weld? Jackson and Krebs defined salt weld as the structure joining two rock bodies formerly separated by salt. So this figure from Jackson et al. 2014 help us to understand this concept. So the pink layer in the geological section is salt. There is also rock deposited below the salt, which is called pre-salt or subsalt, and rock deposited above the salt, which is called supersalt. With salt flow, some areas of the salt body can get thicker, forming, for example, diapirs, whereas other areas may thin, and supersalt and subsalt rocks may come into contact, then forming a salt weld. But there aren't just one type of weld. There are actually three types based on their structural position. So if a weld joins strata originally above and below autochthonal salt, then we have a primary weld. But if a weld joins strata situated either side of a squeezed diapir, then we have a secondary weld. So when a weld joins strata originally above and below allochthonal salt, then it's called tertiary weld. And besides the classification in relation to the structural position, welds are also classified in terms of their completeness or continuity, reflecting the thickness of remnant salt in the weld surface. So in this sense, as illustrated in map and section in the upper part of this diagram, again from Jackson et al. 2014, a complete weld occurs when no salt has been left after the welding. And as shown in the lower part of the diagram, an incomplete weld means that there is a thin zone of remnant salt. And finally, a discontinuous weld contains welded areas alongside areas of thin remnant salt. So also, depending on the observation scale, for example, seismic, a weld is called apparent when it seems to be welded, but in reality, there is a thin zone of salt left on the weld surface. So why are salt welds important, and why do we want to study them? So it's because welds are important to reconstruct the geological evolution of salt-bearing basins. So understanding the timing of weld formation helps understand the original thickness of salt layer. Also, welds has an impact on the evolution of the basin after their formation, as they may restrict salt and overburden to translate horizontally. They are also important because the rheology and composition of the remnant lithology in welds may impact prospectivity, as in some cases, welds can trap and seal hydrocarbons, as in this example of an accumulation under a tertiary weld, while in other cases, welds allow fluids to migrate across them and reach reservoirs situated in upper levels. So welds can also control the flow of hazardous nuclear waste stored in nearby salt diapirs. And finally, welds may play a role in the ability of salt tectonic systems to act as CO2 repositories. So given that context, what do you want to know about salt welds? So we are interested in the variability of thickness and composition of salt welds, and how this relates to bulk thickness of the evaporitic interval. Which factors controlling the capacity of salt welds to transmit or seal fluids, and the effect of welding on physical properties of adjacent rocks, and how could it impact seismic imaging, reservoir quality, and trap definition? So to answer the first question, today I'll be presenting a subsurface case study from the Sulphur North Sea and UK continental shelf. In this case study, we looked into the Zaxton upper Zaxton supergroup from the upper Permian in the UK continental shelf.
Gabi,
Yes?
sorry to interrupt. Do you have a microphone? Some of us are listening loud and clear, but some of others have problems listening to you. So do you have a microphone? Like, can you talk closer to the microphone?
My microphone should be from my headset.
Oh, okay, part of it. Okay. Yeah, maybe just speak a bit louder. I mean, you can continue where you are. Sorry for the interruption.
Okay, no problem. Let me see if my microphone is. Okay. Now I changed it to my headset microphone because it was in a computer audio. I think that was.
That's better. Yes, it's better.
So sorry about that.
That's okay. Okay, we'll let you continue.
Do you want me to come back few slides?
That's okay. Yeah, I think it should be okay if you continue with with the slide. What do you want to know? Yeah, should be okay.
Okay.
Maybe just start there and then Thank you. Thank you.
No problem. Thank you so much. So given the importance of salt welds, what do you want to know about them? So we are interested in the variability of thickness and composition of salt welds, and how this relates to bulk thickness of the evaporitic interval, and which are the factors controlling the capacity of salt welds to transmit or seal fluids, and what are the effects of welding on physical properties of adjacent rocks, and how could it impact seismic imaging, reservoir quality, and trap definition. So to answer the first question, I'll be presenting a subsurface case study from the Sulphur North Sea. In this case study, we looked into the upper Permian Zaxton supergroup in the UK continental shelf, based on well, 2D and 3D seismic data. From our data set, we used well data to understand the intra-Zaxton compositional variability by developing a petrophysical characterization workflow based on 3 interpretation methods with validation steps between them to interpret a set of 103 wells. So I will now go briefly through each of these lithological interpretation methods. So the first method used was based on identifying lithologies with petrophysical signature compatible with the typical log response for each lithology expected in the Jackson supergroup. So basically the aim here is to first pick the easiest identifiable zones, like the most obvious ones, in which our interpretation confidence is high. So to do so, we used gamma ray, density, and sonic logs to define cutoffs or range of values centered on the typical log response for each intra-Jackson lithology, as we can see in this table here. So for example, halite, we defined gamma ray values between 0 and 30 degrees, density values between 1.9 and 2.2 grams per cubic centimeter, and sonic values between 64 to 72 microseconds per feet. So every zone with a log's response meeting these three criteria were interpreted as halite. So as the log response for these zones are the same of the typical log response for a given lithology, then we are pretty confident in our interpretation. So also important to mention that we based these cutoffs on work from Rodriguez 2017, Jackson et al. 2018, Warren 2018. But we also adjusted these values according to core data available. So we applied these cutoffs for all the 103 wells available, and where all the three search criteria were met, a lithology was assigned, represented by the colored zones, and stored in this log that we called calculated litho. But as you can see, there are some blank zones, which are the zones where no lithology was assigned because at least one of the three petrophysical criteria were not met. And this is expected, right? Because the typical log responses are defined based on pure lithologies, and they are in fact heterogeneities related to the presence of impurities or mixed lithologies at mineral scale. There might be interbedding thinner than the vertical resolution of the logging tools and so on. So after doing this, we've got a significant portion of all wells interpreted, but some zones missing interpretation. So to fill the gaps or these blank zones left by the cutoff-based interpretation, we selected 26 wells to conduct a detailed cross-plot based interpretation. So for each of those 26 wells, we used a cross-plot of density in the x-axis and sonic in the y-axis, with data points colored with gamma ray, like in this upper cross-plot. And we also used the same cross-plot, but with the points colored with lithologies assigned by the previous interpretation method, and we compared them. So this approach helped us to easily identify petrophysical clusters related to each lithology. So let's take an example, this group of points, which was interpreted as halite. So all the pink dots here represent halite interpreted by the cutoff-based method. And this blank point called Y is within a cluster with similar petrophysical properties of that point X, which was assigned as halite. So the point Y was assigned as halite as well because they share similar petrophysical properties. So the results of this method were stored then in a second log called interpreted litho. Then by doing this, we fully interpreted these 26 wells, so no more blank zones left in those 26 wells. However, we are dealing with a large data set. Then to interpret the remaining 77 wells, we chose a statistical, more robust and less time-consuming method, which is cluster analysis, using the K-means algorithm to fill the interpretation gaps in the remaining 77 wells. And we used the portions interpreted by cutoff-based method and the 26 fully interpreted wells as a calibration to the statistical method. So basically, this method splits the data set into a given number of clusters in a way that points inside each cluster share more similarities with other points inside the same cluster than any other. So again, we used gamma ray, density, and sonic logs as input to the cluster analysis. So we can see the resulting clusters in these cross plots of gamma ray, density, and sonic. And once the clusters were defined, the lithologies interpreted in the previous steps were used to calibrate the analysis. So the calibration consists of calculating a weighting factor for each lithology, which takes in account the distance between each point in the calibration curve and the cluster mean. The cluster means are the black circles. And the lithology with the highest weighting factor is the most likely lithology. So the calibration results are summarized in this bar graph, in which the clusters are represented in the rows, and the lithologies associated with them, so the most likely lithologies, are in this column. So the lithology log generated by this method was then used to fill the remaining gaps of interpretation in those 77 wells. And then once we finished this interpretation method, we've got all the 100 wells interpreted, and we've got the exact same compositional variability sorted out. So now we are going to look into the exact same thickness variability. And to do so, we generated thickness maps, exact same thickness maps, based on seismic interpretation for those 4 areas. And then we defined salt structural domains. We defined 2 basic salt structural domains. One is a thin salt related to welds and thin deposition in structural highs and basin margins, and a thick salt domain related to salt pillows, diapirs, and walls. I'll now show some seismic examples and well sections from the area 2, which is covered by a 3D survey around the salt pit basin, to integrate then the thickness and compositional variability of the Zexin supergroup. So this is a thickness map of the Zexin supergroup in the area 2, with thin salt domains highlighted in white and thick salt domains highlighted in black. Wells are shown as red dots, and the yellow line is a seismic section that I will show in the next slide. Okay, this is a depth migrated seismic line. The base of the Zexin is represented by the purple horizon, and the top Zexin is represented by the pink horizon. In the middle of this section, we can also note a primary weld. And in terms of structural style, welding here has been generated under compressional seating, as evidenced by the buckle folds and the squeezed diapirs. Now let's see a well section along that same seismic section I just showed in the previous slide. So note there's a well crossing close a primary weld, and 1 well crossing a salt diapir, and 2 wells crossing a salt pillow. So from the interpretation of those wells, we note that the middle and upper portion of the Zexin interval is rich in halite and other mobile salt, such as carnallite and tachydrite. And the thickness of this mobile salt dominated unit is variable and directly correlated to the zechstein gross thickness, which is this upper unit is thicker in diapirs and thinner in welds. So we can also note a basal unit compositionally distinct from the upper unit. So this basal unit is rich in mechanically strong layers, including carbonates, anhydrite, clastics, and minor polyhalites. Additionally, the thickness of this basal unit is fairly constant across different salt structures. For example, in those two wells with contrasting zechstein bulk thickness, one crossing a diapair and another one crossing close to a weld, the thickness of the basal unit is fairly constant, while the thickness of the upper unit, dominated by mobile salt, is thicker in the diapair and thinner in the weld. So now let's zoom in that well close to the weld. Here is the Lyotological interpretation for this well. And here we have the basal unit, the basal section rich in strong brittle layers, and the rest of the interval is dominated by halite with thin layers of carbonates. And in this pie chart here, we can see the proportions of intrazechstein lithology. So halite represents around 39% of the zechstein interval, followed by carbonates and anhydrite, clastics, and polyhalites. So if we translate lithology proportions to mechanical behavior, we will see that mobile salts represent 39% of the evaporitic interval, while rigid layers represent about 61%. Now, let's see how lithology proportions in this well compare to other wells crossing fixed salt domains. So it's notable the higher proportion of halite and other mobile salt in fixed salt domains. Mobile salts, in this case, counts for 78 to about 85% of the zechstein gross thickness in fixed salt areas, meaning in areas where we have salt diapirs or salt pillows. And it corresponds to just around 39% in areas of thin salt and close to a weld. So we just saw one example crossing one specific seismic section. But how about the big picture? Is that the same pattern present? And yes, it does. In this bar graph, we have the all 103 wells represented. Each bar corresponds to a well. On the left-hand side, we have the zechstein gross thickness in meters, and the pink interval represents mobile salt, while the white interval represents other lithologies. So on the right side of the graph, we have the percentage of mobile salt within the zechstein, and the yellow dots represent this percentage for each well, while the dashed black line is the moving average of the percentage of mobile salt within the zechstein interval. So there's clearly a general increased trend of mobile salt as zechstein gross thickness increases. So meaning structures such as diapirs are enriched in mobile salt, whereas welds are depleted in mobile salts. Also, a moving average of the basal unit thickness is represented by the dashed purple line. The thickness of this unit rich in rigid lithologies presents subtle variations, probably reflecting the positional features. So to conclude, across different salt structural domains, the base of the zechstein supergroup is dominated by mechanically strong layers such as anhydrite, carbonates, and clastics. And this mechanically basal unit presents subtle thickness variation across different salt structures. So regardless if it's a weld or a diaper, indicating an autochthonous character. The autochthonous character of this unit suggests that these rigid layers were not involved in salt deformation and were not removed by salt flow. So some reasons might be because of the boundary drag effect, which means the flow velocity is lower on the borders of the evaporitic interval, so it is harder to remove material from this area close to the border. And also because of this basal unit might have coupled with the underlying clastic-dominated rocks from the Rotliegend group due to their similar mechanical behavior, as this basal unit is mainly composed by brittle, rigid layers such as carbonates and anhydrite. And also, primary welds in the sulfur North Sea are mainly composed by those mechanically strong layers with autochthonous or depositional character, and are also depleted in mobile salt that flow away into nearby diapirs by a process called differential purification by movement. So to illustrate this, if we have a primary multi-layered evaporitic section, as it thins, the rigid base keeps immobile while the mobile salts start to flow away. If the thinning keeps going until welding occurs, we will have a unit with the intact strong base and an upper section depleted in mobile salts. Meanwhile, a nearby diaper will inflate and be enriched in mobile salt. So the predominance of brittle immobile layers in primary welds may be favorable to the existence of migration pathways across them, and may also influence how the deformation is absorbed by adjacent rocks. Also, rheology and the original evaporitic deposition is key to determine salt welds composition and thickness. And now, what's next? So, future work based on subsurface data will investigate how different tectonic regimes impact the geometry, thickness, and composition of salt welds in the Zexen supergroup. So, for example, viscous flow modeling undertaken by Wagner and Jackson 2011 suggests that shearing in the welding surface may favor the complete removal of salt. So we want to know if natural examples would support that hypothesis. Also, we are planning to undertake field work at the Atlas in Morocco later this year, if COVID permits, of course. And for this field work, we intend to document the lithological composition of welds in different structural configurations, so in primary and secondary welds, and also to investigate the deformation and evidence of fluid flow associated with these structures. Finally, we use geomechanical modeling to understand the effect salt weld has on physical properties of sub and suprasalt strata. So existent geomechanical models have analyzed the stress variations in mini basins created by downbuilding above a flat salt layer. So possible configurations to be tested in our model are variable sedimentation rates during welding, shearing in the on the welding surface, and welding of a mechanically heterogeneous evaporitic sequence. Yes, so I think that's all, and thank you so much for joining, and I'll be happy to take any questions.
Thank you, Gabby. Awesome work.
Thank you.
I'm so impressed that you're working with 100 wells. It's like, oh my God.
Yes, it's really, oh my God.
Exactly, because being a seismic person, you know, had 8 wells, you know, to look at the lithology within the Santos Basin, and that was good enough for me. So that is, yeah, awesome work. I'm really surprised. Did you have many issues with the wells, like, you know, doing the QC in the beginning and the loading?
Yes, yes, they were actually loaded in the project when I got them, but the QC was such time consuming. So it took a lot of time from my project, and to put everything on the same standards, to understand the resolution for each of the logs, and you know, to put everything the same and at the same standards to finally start interpreting them. It was really difficult. And other than that, we've got reports and core data, but the information was spread around. Then, yeah, it took a while to organize everything.
Exactly. It takes a lot of time, you know, integrating QC.
Yeah, and that's why we ended up creating 3 different methods in this workflow, because we were seeing how it worked best to tackle this big data set.
That is awesome that you're documenting the workflows. I think is great, because it helps for the other students. It's awesome. We have a question here from Mike Hudek. Did any of your wells pass through the thinnest areas of salt, apparent welds on seismic? If so, what happened to the basal unit there?
Can you repeat, please?
Yes. So did any of your wells pass through the thinnest areas of salt? So any apparent weld on seismic? And if so, what happened to the basal unit there?
Okay. Yes. So the well crossing the thinnest area. So I haven't found in this data set any well crossing like a complete weld. So even the thinnest areas, I found lithology left, and I think the thinnest thickness I've got, it was maybe about around 70 or 8 meters, and the basal unit was there with pretty much the same composition, and just a little bit less thick than in general, but it was around that average. So that was just a subtle variation. That was not an important, significant thickness variation of the basal unit, even in the thinnest south area.
Okay. Thank you, Gabby. Hope that's clear, Mike.
Yeah.
Let us know.
Yeah, thank you. And I think that's why we think this basal unit might have not been involved in south flow and have this autochthonous character, because regardless if we are in a thick south area or a very thin south area, we see the same compositional pattern and pretty much same thickness.
Okay. We have here another question from Mark Rowan. Nice talk, Gabby. I have seen seismic data the Red Sea and Gabon that suggests that the basal strong layer can in places be disrupted and included in the mobile salt. The result is this continuous bright amplitude along the base salt. Do you see anything like that?
Yes, in terms of seismic, we see in some areas some discontinuities. So with the well data, we didn't see much variation, but if we could undertake any seismic inversion or seismic attributes to try to trace the information we have from wells across the seismic, we could find maybe more variation, because in some areas there are these discontinuous patterns. And yeah, I see some discontinuous patterns, but I don't have any other analysis, or I have not undertaken extra work with the seismic to check if there's these inclusions.
Yeah, okay. Yes. So good thing
Yeah,
to
but interesting to hear that this occurs in the other basins.
Yeah, North Sea and Gabon. I think it is possible, definitely, that you find some of these disrupted evaporites, and it's very clear in the seismic.
Yes, that is something that I was talking to a colleague other day. That's something that we might try to represent in the modeling. I'm not sure if in the numerical modeling, but maybe someone else can do this research using physical modeling to see how disrupted this basal unit could be under different situations, under welding, when you have shearing during the welding, and also we can try to represent the deposition, some depositional features still remaining in this basal section. So I think there's interesting research to be done in this sense.
Yeah, it's a great idea. So we continue with the questions. We have one from Tim McIntyre. Do you see any evidence of fragmentation of intrasalt strata, or do you think that all carbonate clastic units accumulate in the primary welds?
Evidence of cementation?
Fragmentation of intrasalt.
Fragmentation.
Yeah, that's more.
Okay. Yeah, so this is something we want to check in the field work, because from well logs, they are just conventional well logs, and you're not able to see any kind of fragmentation, and also with the seismic resolution, it's not possible. Even though we have cores in the Zechstein interval, they are not on the welds, and they are in the wells crossing thick salt. But in our field work, if that happens, we would like to check if for fragmentation on the weld surface, if there is any lithologies left, and also fragmentation of sub and suprasalt, and to document the deformation on the surrounding the weld, because one thing we want to test is how the composition of the lithologies left on weld impact the deformation. Because if you have halite on the weld, it can absorb more the stress, or maybe if you have just carbonate and anhydrite, maybe can they dissipate easier the stress, or they can fracture easier. So on one hand, there are some work suggesting that the stress increases on surrounding the weld, so rocks may get more compacted, but do they get more fractured, more fragmented? So far I don't have this answer. So we hope with field work we could understand that better.
Yeah, that is amazing. You'll be able to integrate field work. It's gonna be great.
Yeah, hopefully.
It will. Yeah, it will happen.
Yeah.
So we have, okay, so I'll do it another from Kamaldeen Omosanya. Nice talk. My question is also related to Mike's. I wonder if you constrained your seismic interpretation using well tops from the wells, assuming all the wells intersect the top and base of the salt. Thanks. You use wells, right? You constrain your seismic interpretation.
Yes, I constrained. Yes, so I've got top and base salt of the exact same. From the wells, we did synthetic seismograms, and also the seismic survey I showed it was in depth, but for other seismic surveys in time, we took synthetic seismograms, and we've got the stratigraphic markers from the reports and from cores and all the available data.
Oh, that is awesome. So you had to do synthetics like for many wells, or were you able to do for all of them? Or?
No, not for all, and I just select some key wells.
That's hard work. Yeah, it's good. Okay, so we have I think Leo wanted to join the Q&A, so it would be nice. Leo, are you there?
Hi, Clara. Yes, you think you need to make me host so I can open the video?
Oh, yeah, sorry. I was here, so.
Yeah, Clara, what's the last the last question was?
Okay, so we are Western Moriac. So I saw he was there. I'm like, okay, let's leave the Brazilian discussing.
Oh, wow. All Brazilians at once.
Yeah, so it's nice to see the big names joining Gabi's talk. So I'll stay here just in case, to enjoy this.
Hi, Gabi.
Hi, Leo.
Yeah, hi, everyone. Gabi, thanks for the talk. It's great to see you. I actually just typed the talk as Clara was talking, introducing me. So yes, right, so I'm going to follow up and carry on with the questions. So yeah, from Webster Moriac. So Gabi, very interesting talk. In the South Atlantic, there are some cores that indicate brecciated rocks at the base of the soil layer. Do you have any cores in the North Sea showing basal shear, basal shear?
Thanks, Webster, for the question. Yeah, unfortunately, the cores are not in wells crossing wells. The cores, they are in thick salt area. But there is something that we are definitely looking for to see in the field work. There's evidence of shearing.
Okay. I actually have a question there. So my question also I think relates a bit to what Mark mentioned. I think so. Do you think the preservation of the basal units in the North Sea could be related to the fact that you don't have so much basal shearing because you are in a more vertical dominated salt tectonics, like load-driven salt tectonics setting, as opposed, for example, to passive margins or have lateral, like multi-kilometer translation, lateral salt tectonics, like Brazil, West Africa, Red Sea, Gulf of Mexico? Do you think it could be different, the degree of preservation, or do you have any insights on that?
Yeah, I think so. I think it could be different, even though there is compression in the North Sea because there are squeezed salt walls and squeezed diapers. There are buckle folds, but you see a lot of those, as you said, more vertical salt tectonics, and I think the horizontal component is not that important as it is in a continental margin or in a convergent margin, because if you have that, like the loading in the continental margin or the extension, I think the structures will translate more easily, and maybe these units can be easier removed. And I think it's also something to do with the original stratigraphy of the North Sea, because there's those Zechstein 1 and 2 units that they are composed by those rigid layers. But I wonder in a different basin in which the stratigraphy is a bit different, and where you don't know such important carbonates or anhydrites layered at the base, if you have less thickness left on welds.
No, I think it makes sense.
So we definitely want to include in the numerical models shearing and on the welding surface and see how the difference it makes.
Yeah, I think that would be really good for you to explore with the not physical, well, physical as well if you had time, but with the numerical models, the different settings. So how the welds, I don't know, would vary in the different basinal settings. So passive margins versus extensional bases or convergent salt tectonics. But yeah, thanks. Now that clarifies a lot. So the next question from Hector Barnett. Great talk, Gabi. Just curious as to if you've looked further into how the differing soil units within the Zechstein line, Strasfoot, Aller, I don't know if I'm saying that right, behave differently in the welds. As the Z2 salt tends to be the most mobile salt units, is this reflecting the amount of each unit left in partial welds? I can read that again. Sorry, if you yeah. So just curious as if you looked further into how different soil units within the Zechstein behave differently in the welds. And then the Z2 that tends to be the most mobile units, and if this is reflected in the partial welds.
Yes. So I think it will reflect somehow on the welds, because there are those nomenclatures, those stratigraphic units well documented in Zechstein, and I don't remember exactly which of them are the most mobile ones, the most rich in halides, because in our work we try to separate by mechanical behavior. We didn't use much that stratigraphic nomenclature, but we think if there's an area where the original stratigraphy is, the Zechstein is richer in more mobile units, then it will affect the resulting weld. I don't know if I answered that.
Yeah. I think, I mean, yeah, I don't know that much about the Zechstein stratigraphy, so I can't really comment on that. But yes, I think you answered that. That's fine. So let's see who is next. I don't think we have any more questions on the. I know we have another one from Chris Brennan on the Q&A. Hi Gabi, great talk. Do you have any indication from the overburden on the timing or the formation of the salt welds across the salt pit and the silver pit basins? And do these welds form around the same time, driven by regional tectonics, or are they isolated areas of salt withdrawal alokinesis welding at different times throughout the Mesozoic, Cenozoic?
Okay, very interesting. Yeah. So I still didn't go much further in the kinematics and the structural evolution of the welds in the area, but there are some interesting work. One of them is the MSc last year from Hector Barnett that just asked the question about intra-Zechstein tectonics, and there are other research being doing, for example, by Amir here from Imperial with Leo, you and Chris Jackson,
yes.
about intra-Zechstein tectonics. So there's some evidence that the salt tectonics in the Zechstein started even during the Zechstein timing, but there's also salt tectonics that occurred later in Triassic and Cretaceous time, but I haven't yet gone into detail to get the timing of the salt welding in the area. That is what I still need to do in terms of my subsurface part of my project, is to analyze the timing of the weldings, to do more detailed structural characterization of them and understand how compression and slightly different tectonic systems will impact salt wells. So yeah, don't still have robust questions, but I think the timing of the welding, the textile tectonic indexing spans quite a bit.
Yeah. I mean, it's something that you plan to investigate in your PhD, but you don't have the answer yet, but I'm sure you have by the end of the project. It's something that you'll be interested to see. And yeah, so we have another question. I think it was a follow-up from the previous one from Tim McIntyre. So he says, I think I was not clear of my question. I was wondering if you see large kilometer scale fragments of ventral salt strata like the carbonate stringers, Noman, or the Ekai in the Katangan Basin. Yeah, so for example, if the carbonate fragments, you might expect, so see large variations in salt weld thickness, even where all the mobile salt is evacuated.
Okay, now I got your question. Sorry, I think I really didn't understand quite well previously. Yes, so in Zaxxon there are a lot of stringers, some units with rigid units that are less viscous units. So it's very common to have anhydride and carbonates encased in salt pillows and salt diapirs. For example, that well that I showed crossing a salt diapir, there's a very important string of anhydride. And they also show interesting structures. So they evidence compression, and they are sometimes fragmented. It's possible to see endoseismic, but what seems is that those stringers are from intermediate levels in the stratigraphy. I haven't seen yet in the seismic those carbonates or those more rigid layers from the basal unit showing that fragmentation or that disruption and being encased or forming such stringers. So as far as I saw in the seismic data, I haven't seen that, but what I saw are those stringers from intermediate layers, because the upper sections, they are not just mobile salt, they are richer in mobile salt, but there are also layers of different compositions, and they do form strings which fragment.
Okay.
And by the seismic scale, some of them are huge, are very important fragments, but don't have evidence for the basal unit to create same fragmentation pattern. Yeah.
Okay. Yeah. No, that makes sense. I think from what you presented, you expect the basal units to be less deformed and fragmented as well for the setting as well. Yeah, he said, thank you, excellent talk. So I think that's answered. So let's see the chat. I think we also have a couple of questions in the chat. Let me just check here quickly. Okay, so the first one from Hank Combrink. How about more competent layers from within the Zaxxon? So carbonates, they occur in between two more mobile layers. What happens to those once the salts are starting to move both above and below? I think you kind of answered that, but yeah, if you want to comment.
Yeah, I think that's what we were just saying, that they create those stringers, and then depending on which level of the stratigraphy they are, even though if they are rigid, if they are in the center of the flow, they might be encased, and they can also flow away encased by the more viscous layers.
Yeah. Okay. Yeah. You've answered that already, I think. So the other one from Mark Fisher. Do you have any information constraining the deformation or character of strata immediately beneath the base salt, beneath welds? Are those strata pristine or highly deformed, or something in between?
Well, I don't have this from my work, but I just know that the stratigraphy below is the Rotland's group. which are the classic dominated rocks, and there are works from Howitt et al. From 2011 that they undertaken geomechanical modeling in the North Sea, and they look at, but I think they used more data and sonic data to see proper change in the Triassic, which is above the salt. I'm not quite sure if they looked also into physical properties change underneath the salt in the rock ligands. So that's something that we are very interested to know, is that the strata below the salt underwell will be more compacted due to stress anomalies, or is that going to be more fractured? So I think that we still need the field and modeling data to answer that, and maybe that's answered by the Howitt's paper, but I'm just not quite sure now.
Okay, yeah, yeah, that's fine. So I think in terms of question, that's it. I think we have a comment from Guido Hotz, says, watch out for...
He's the author I just mentioned. Yeah.
Okay, yes, so he says, watch out for tuning effects. They impact the seismic expression too. And he also says, you also see below the salt, you see extra compaction. So yes, he just confirmed.
That's great. Yeah, that's great that he answered.
He answered the question for you, yeah.
Yeah, that's great. And yeah, the tuning effect it might be really possible. So there's a very interesting PhD thesis that looked at seismic response for salt welds, and that was by Wagner, 2010. And so he classified 4 types of seismic response for in salt welds. Then it will depend, according to his seismic modeling, on the magnitude and polarity of the sub and suprasalt rocks. So there are basically those 4 guiding types to interpret the seismic response in salt welds, and tuning is definitely an important effect. So I think I have the full reference for this work here that I can just quote.
You can put in the chat, yeah?
In the chat,
yeah.
Because this, I think this definitely would answer.
Yeah, that's very useful. Yeah, we appreciate it. I think everyone.
Yeah.
All right, great. Yeah, thanks, Gabi. So the last question, apparently, I think that's the last one. So it's from Piotr. Please check. There was some subsalt faults shown on your seismics. Do you think they might have been active during the position of the Zechstein?
The subsalt? Could you please repeat?
Yeah, so there are some subsalt faults in your seismic. Do you think they might have been active during the position of the Zechstein?
Actually, I haven't looked at them in this sense to properly understand the timing of those faults. But there are many inverted faults in the Zechstein, in the Permian Basin, due to posterior compression. So I'm not sure if those pre-salt faults were also reactivated, or if they were active during Zechstein.
Yeah.
So yeah, I'm not sure now.
Yeah, I think in other words, it'd be like if the Zechstein is seen extension to those normal faults, to the pre-salt normal faults.
Yeah, I don't think that.
It's hard to answer this kind of question, isn't it? I think it's hard to answer in most basins. But yeah, I think that's it. I don't think. Let me just double check if I have any other questions.
I have a quick question, if I can squeeze it in.
Oh, hello, Connor. Yeah, I will stop the video, and then you can, if you want to put the video.
No, it's fine. Just well, great talk, Gabby. Really enjoyed it.
Thank you.
In your very nice graph where you looked at the percentage of mobile salts relative to the total thickness of the Zechstein group, I just remember the yellow dots, they were the percentage of mobile halide in the total column, yeah?
Yeah, mobile salts, yeah, halide and carnallite are the mobile salts.
So they kind of, in my memory, they kind of were almost split bimodally, and you had a lot of them along a line which were like 90% mobile halide, and some were hovering around like 50, 60-ish, I think. Why is there a reason behind that sort of split in that quite distinct split in the percentage of mobile halide that was left in the Zechstein?
I think so. Maybe I will share again that slide so it's easier to. Let me just put in. Yes, so there's like that increased trend here, and then you have a very different pattern for those ones. And I think these wells, they are more related to structural highs,
Cool.
where there was, it's not, they're not welds, so there was just basically no Zechstein deposition in structural highs or basing margins. So this is really a different pattern from this.
It's like a deposition feature.
Yeah, I think this is like very low mobile salts proportion, because they are or in structural highs or basing margins, but some of them do belong to welds, very few of them, and I still don't know why. Since there's a threshold that after certain Zechstein gross thickness, then you get this pattern very clear, and below this thickness, that is not so clear. I think there's that interference of the wells in structural highs and basing margins, but it's also still to be investigated.
Okay, cool. Thanks.
Thank you.
So I was muted. Yes, so I think we can wrap up and conclude your talk. So again, on behalf of everyone of us in the TIG and also all the participants, I'd like to thank you again for the great talk. Gabi, it was really nice. It's nice to see this work coming together and the progress of your PhD. It's really interesting stuff, really relevant as well. So yeah, wish you all the best of luck doing the PhD, and I hope we can get to go to Morocco to do the field work. It should be a lot of fun and very useful. And yes, thank you everyone for joining us. Please, if you have interest in submitting a manuscript for our special publication, please let us know by the end of April, by the end of next month, and with a preliminary title of your work. We already have really interesting papers already from interesting big names, as well as variable types of work. So if you're interested and you want to be part of that publication, please let us know as soon as possible. And that's it. I don't know if Clara, Connor want to say anything else.
No, thank you for joining. Thank you to Gabi for presenting. It was great. I really enjoyed that. Close to my heart. That was awesome. Yeah, it's really great work.
Talk. Thanks, Gabi.
Yeah, it was great.
Thank you, Gabi. So nice to see you.
Thanks so much, everyone. Yeah, that was
fingers
so
crossed
nice.
for that field work. Hope you get to go out to the Atlas.
Yeah. I want to go too.
Yeah, if you need
Yeah,
field
this will be
assistance,
amazing.
Yeah, let's go together.
Yeah.
We help you.
That
bye
would be
everyone.
amazing. Yeah, thank you
Yeah.
so much. That was
Thank you, Gabi.
really
Thank you,
wonderful.
everyone.
Thank you.
Bye.
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 Thanks,
Take
guys.
care. Bye bye.